Let's talk about velociraptors. Woo! The first thing to know about Jurassic Park velociraptors is that they are not velociraptors. So, Jurassic Park velociraptor is designed after its cousin called Deinonychus. In the early 90s, Deinonychus and velociraptor were gone back and forth, and who's which one or whatever. But Crichton decided to design them after Deinonychus, but call them velociraptor because velociraptor sounds a lot scarier. In reality, velociraptor was no bigger than a turkey, right? So a modern day turkey. So you could potentially kick velociraptor as it comes at you in the kitchen. I'm 6 feet tall, right? So it wouldn't come any higher than my hip, most likely, right? A full-grown velociraptor. Deinonychus was a much bigger cousin, but even bigger than that in the early 90s was described a bigger sister, bigger cousin called Utahraptor, right? And we can see on the screen, Utahraptor was much bigger. So it gave some credence to Michael Crichton's large apex predator kind of scary thing, right? As we can see on this slide, the biggest thing that all Jurassic movies get wrong is they don't give them feathers, right? These are all dromaeosaurs, which is the group that velociraptors belong to. Dromaeosaurs, of course, had feathers. There's fossil evidence with quill knobs to show that these animals did have feathers. They weren't for flight, they were more for body warmth, keeping a nest of eggs warm, maybe just balance while it was hunting prey and things like that, right? Next slide. So let's talk a little about where our velociraptors fall in our family tree, right? So in our dinosaur family tree, you can see on the left is the ornithischians, or the bird-hipped dinosaurs. Those are not the dinosaurs that birds came from. So don't get that confused, right? Bird-hipped, no birds. Saurischans, our lizard-hipped dinosaurs, that's where we get birds. So our larger group of saurischans contain sauropods, our long necks, our little foots from Land Before Time, and of course our theropods. Those are our two-legged meat eaters. And from our theropod chain comes our birds. And much like birds, actual velociraptors had more gracile features than they have in the film, right? So in the film, Jurassic Park, velociraptors are built like NFL linebackers, right? They've got big heads, broad shoulders, they're terrifying. In reality, we know they're all only as big as a turkey, but they would have had a much slender face, thin bird-like bones. Their hands wouldn't have been kangaroo-style praying mantis hands, right? They actually would have been faced more palms forward. And they had an extra bone in their wrist that allowed that hand to fold under a little bit like a bird's wing, right? So it could kind of fold in like a bird's wing. So their ability to open doors just right out. We also, hopefully, maybe, right? It's a film, that's a scene that stuck with me. When Dr. Grant terrifies a small child at his field site with a velociraptor claw, right? He threatens him with pack hunting behavior, and this animal would have disemboweled you without thinking about it. Well, all of that is wrong, right? So in the early 90s, there was a belief that velociraptors were pack hunters, and there was a belief that that claw was used for slicing and ripping apart prey. It would have actually been used more for grasping, and we now know that these animals did not live in a family unit. There's evidence to suggest that the juveniles ate different food than the adults, so that means they were not living together, they weren't hunting together, right? They're living as solitary hunters. The biggest thing about velociraptors was their intelligence, right? Dr. Grant talks about they were going to take over the world if they didn't go extinct, right? Well, that's also wrong. I'm just here to ruin everybody's day about Jurassic Park, right? That's also wrong. So let's talk about velociraptor intelligence. This chart shows us a graph of intelligence put to numbers. So this comes from measurements of brain mass to body size, and there's some log transforms and some other things we do to get these numbers. But the closer we are to zero, the smarter we are. So up here on the high end, we have our most intelligent people right there on the high end, Homo sapiens. Down a little further, we have African elephants. All the way down at the far low end, we get our herbivorous dinosaurs, Triceratops, Brachiosaurus, right? They didn't need much intelligence to just graze and survive. And then here in the middle, we have our smartest dinosaur. This is Stenonychosaurus, so Velociraptor is not on this chart, but Stenonychosaurus is a troodontid, and troodontids are believed to be the most intelligent dinosaur. And here on our chart, they fall somewhere between a goldfish and an ostrich. So the Velociraptor wouldn't have actually been smarter than a chicken or a turkey. So not only would its hands not have worked to open the door, but it wouldn't have even been smart enough to figure it out. That's not to say that it needed that intelligence, right? It's just a predator. The intelligence of a turkey is enough to get by in the Cretaceous, right? Let's talk about the big one. So T-Rex, right? It's got a very big pivotal moment. The big scary T-Rex paddock scene. The glass of water vibrates on the dashboard, right? Well, that's also wrong. T-Rex was mostly correct as far as Jurassic Park was concerned at the time, right? A lot of what they did with T-Rex was correct, but they wouldn't have shaken the earth while they're walking. First off, if you're a predator and you let people know you're coming by stomping, you're not going to eat very much. Second, we know today that big animals like elephants can sneak up on humans, right? Elephants can walk around and sneak up on people. I'm sure T-Rex could, especially walking on muddy soil, right? That soil would have absorbed that impact and wouldn't have shaken the cars like it did in the film. But a key part in this scene, right, is Dr. Grant yelling for everyone to stop moving. Don't move. It can't see you if you don't move, right? So our T-Rex visual acuity based on movement is nonsense. And then do the next one. Yes, get the eyeballs up there. All right, so T-Rex, we now know, likely had the best vision of any animal ever. Current, alive now, or extinct. No animal could really survive if their vision was only based on movement. Right? If you can only see movement, you can't see anything. I can't walk around if I can't see solitary objects, right? So its visual acuity being based on movement comes a little from the science that Crichton applied, filling in the DNA gaps, and a little bit of comparison to amphibian brain cases and dinosaur brain cases at the time. However, T-Rex definitely had binocular vision like we see, which meant it had great depth perception, so it could tell foreground elements from background elements. It also, there's evidence to suggest they could differentiate color, right? So a T-Rex could actually see different shades of colors, which would be a great benefit for someone who's hunting, right? So not only could it not only see you if you were standing there, it could have smelled you, right? There's all the talk of it being great olfactory senses. It could definitely smell you if you were standing there, and it could definitely see you. So if you're just standing still in front of a T-Rex, it's going to just eat you, right? It's just going to be a quick snack as he goes on about his business. But I'm not going to just ruin everything, okay? Some things were right about Jurassic Park. Up until Jurassic Park, pop culture representations of dinosaurs were oafish, slow lizards that laid on rocks. This is an old painting from the American Museum of Natural History that shows an upright T-Rex with its tail kind of dragging the ground. Jurassic Park was the first time that we see an actual true posture for a Tyrannosaurus Rex. Right? Its posture would have actually been more horizontal, and it would have had that big head full of teeth out front, and the long tail in the back for balance. Right? T-Rex had that big head and those tiny useless arms, and so it had to get that teeth out front, right, so it could attack things. That is the best thing I think that Jurassic Park did, was they actually applied animals to the animals of Jurassic Park. Dinosaurs weren't just treated like movie monsters. They weren't just treated as these slow-moving lizards. They were fast, warm-blooded animals who found a way to survive on this island that they went extinct on, 66 plus million years ago. Right? So in that same vein, they did get dinosaur creation right to an extent. Not the DNA part, we'll get to that in a second. But the dinosaur creation, from a standpoint of them procreating, is true. They did hatch from eggs, right? We have found dinosaur nests with eggs, with mother dinosaurs nesting on top, protecting their eggs. What we don't see is large, bulbous ostrich eggs, right? So they weren't this kind of globe shape. They would have been longer and sturdy, but they would have been kind of long and oval. But that all has to do with some, DNA tinkering and things that something else they got wrong.
Yeah, so once we get past the eggs everything else is wrong when we start to think about dinosaur creation. So, of course, the idea is these insects were captured in amber, and then we got the DNA out. Okay, so let's just think about this for a minute. I'm a mosquito, I happen to bite a dinosaur, immediately go to a tree, get covered in sap, and then that actually gets buried and forms into a fossil. And then now I'm going to try to get that back out 65 million years later plus. Yeah, not so much. So first of all, the odds of even having these types of fossils are huge, right? Like, that rarely happens. It's like 1 in a million chance to become a fossil. So there's going to be very few. Even if we pretend for a minute that we found enough of these fossils, when we start to think about what's actually preserved, it's really only the hard parts, the bones. There's no DNA in there. There's a little bit of evidence that we have some soft tissue in the record, so all of these funny little microscope images are from T-Rex, and it's little bits of blood, maybe little bits of proteins and things, but nothing that's actually DNA that's making up the structure. The other issue is that we know DNA doesn't stick around for very long. So it has what we call a half-life of only 521 years. What that means is every 521 years, half of what I have goes away. So in 1,000 years, I'm down to only 25%. So dinosaurs lived 65 to 230-ish million years ago. I have no DNA left from that point. And in fact, if we look at how old of DNA do we even see, about 500,000 years we have some things from, it's how we know that Europeans have some Neanderthal DNA in them. We have things from horses, mammoths. The oldest that we found, and this is very, very recent, is like in the order of 1.1 to 1.5 million years ago, and that's a couple of mammoth teeth. And so when we look at those, cool, but I still have at least like 64 million years to go to try to get DNA. Not gonna happen. But not only that, let's pretend for a minute, we'll suspend all of that. DNA lasted, it survived in the mosquito. We need a whole sequence to put an organism together. I'm not gonna get that from a handful of little mosquitoes. This is from a year ago. We were getting near getting a complete sequence for humans. There's lots of us that we can take samples from to try to put that together, and we've been working on it for decades. So trying to get that from a dinosaur, even if we could do that, not gonna happen. But let's pretend we did. So now we have to think about how do we start to try to know some of these things. So this is the part where you all get to participate. Excited? Yes? Okay. So, which animal do you think is most closely related to the whales? And your options are hippo, walrus, and shark. So we'll do show of hands. Raise your hand if you think hippo is the most closely related to whales. All right? Pretty good chunk. How about the walrus? Raise your hand if you think it's walrus. Yeah, several for that as well. And how about shark? Yeah. So they clearly look alike. They're both in the water. They got fins. Those of you who picked hippo, congratulations, you're correct. The biologist, yeah, they got that one. So it turns out, right, we can test DNA from all these things, and so it turns out that DNA is much closer between hippos and whales. We can also actually see this in the fossil record. So if we look at our record of how things have changed, it turns out that whales were land mammals, more like hippos, and they evolved to go back to the water. Unlike sharks, which evolved in the water and have been there for millions and millions of years and haven't changed. And so when we start to think about how we relate these things, it's easy if I can test DNA. It's not so easy if I'm thinking about fossils where I don't have that DNA. All right, should we try another one? One more. Okay. So now we're thinking about alligators, and your options are lizard, bird, or bat. All right, so raise your hand if you think lizard is the most closely related to alligators. All right, got a handful. How about bird? That seems to be a popular one. And how about bat? Yeah, of course, Dr. Haas is going to pick bat, absolutely. All right, let's see, what's the answer? Birds, great. So, again, we can see this in the fossil record. We can also see it from testing parts of their DNA and proteins and things. So, why does this matter? Well, when we think about overall evolution, everything kind of starts with fish, then amphibians, then reptiles, and then we get two branches from our reptiles, one to birds and one to mammals, with dinosaurs that in-between step from reptiles to birds. And so in the movie, when they fill in these missing sequences, we use amphibians. Doesn't make a lot of sense because that's several steps away. So it would have been a lot more sense to use either reptile DNA or even bird DNA to try to fill in some of those missing pieces. So one of the things that is going on now, so from the standpoint of creation in Jurassic Park, not going to happen in that method. That being said, there have been some experiments lately where people have been trying to genetically reverse engineer chickens, which are the closest in DNA to dinosaurs, we think, to see if they can adjust the genes. And so what you're seeing here on the left is my classic chicken with a beak. On the far right is kind of that step before dinosaurs, the reptiles with a more rounded snout. Our dinosaurs would have been somewhere in between, and so they changed some of the genes, and you can see this experimental chicken is kind of somewhere in between. It doesn't have a beak, but it's not quite a snout. Now, let me say, these were embryos, so they didn't bring the chickens all the way to being actual chickens, and in fact, one of the authors said, I think they would have been okay, like as chickens, if we got into that state, but we probably need to think about the ethics. Yeah, we probably do. And in fact, this came up in Jurassic Park, and of course, Dr. Malcolm has that great quote of, your scientists were so preoccupied with whether or not they could, they didn't stop to think if they should. And so it did bring up that idea of the ethics behind it, and it's something that we're still thinking about now.
So there are people today still trying to de-extinct things, right? So this is a company or a nonprofit called Revive and Restore, and they're working on several different projects. One of the most famous, a good pilot project, is the passenger pigeon, right? So the passenger pigeon is something that we made extinct, right? We as humans overhunted and changed environments and literally shot them out of the sky, right, so they no longer exist. The last one went extinct in captivity in the early 1900s. So this is a good pilot project for de-extinction, right, bringing something back that we made extinct. However, they're also working on projects like bringing back a woolly mammoth. We were not responsible for the woolly mammoth's demise, right, not directly. There is some overlap with early humans, but it's mostly believed that climate change is what did end the woolly mammoths. So there is talk of bringing back woolly mammoths. They're trying to work on sequencing that DNA and all those things that Jurassic Park said we shouldn't do, right, to bring back woolly mammoths. These large elephant-like animals walked around mid-America. They want to put them back in mid-America. So I don't know how I feel about walking around with mammoths running around, but those are all ethical considerations, right? We need to make sure that if we're thinking about de-extinction, we take that lesson of Jurassic Park with us when we're trying to do these kinds of things in the 21st century. And so with that, I'll open this up for questions.
So go ahead and ask, raise your hand if you have a question. We can answer questions, but as you're thinking about your questions, please make sure you go ahead and fill out your comment cards. We will be coming around to collect those. Those are going to be used for a drawing for tonight, which I'm not going to lie, has the coolest stuff in it yet. There's Legos. There's a 3D printed Tyrannosaurus Rex skull. There's a great book So, fill that out, but we need some questions in the meantime. So who has a question? All right, stand up.
Why is it that even going back to childhood, before Jurassic Park, children have always been fascinated by dinosaurs? Why is that the case? Have you any thoughts about that?
Right, I've got thoughts about pretty much anything, but something about dinosaurs, right? There's a few things that kids always love, right? Dinosaurs and space, right? It's kind of those two things. You're either a dinosaur kid or you're a space kid, and that can kind of be your step into STEM. So from that standpoint, I really like that kids like dinosaurs. A lot of the thought behind it, right, is, in my opinion, is that they're not around, right, except for birds, right? Birds are dinosaurs, right? But we don't think of birds as dinosaurs. So they're these, look at that. We don't have anything alive that looks like that. And so to get to go to a museum and see this monster that, you can imagine walking around. Me as a kid, I fell in love with paleontology from Jurassic Park, right? I loved it. And part of that draw is these animals aren't around anymore, but it's a gap in science that I can focus on and I can fill in. So from a personal standpoint, it's the, charisma of these extinct animals of, there's nothing like this around, so let's go and look at these scary monsters.
We had another question, which is, how do you know the half-life of something? Our resident
All right. Well, there's a few different methods to understanding the half-life of radioactive isotopes. I actually don't know how that applies to DNA necessarily. But one way is to just put some material in a box and let it decay for a while and see how long it's been, and then you get statistics and you just kind of add that up. And then there's other ways to sort of verify these things. So we have one of the oldest records is from Pliny the Elder, who watched Mount Vesuvius erupt. Was that 79 AD or something? And it was recorded. He wrote it down. He said, "I watched the volcano today," and now we can go and pick up rocks from that volcano and use radiometric dating to determine, and it matches precisely. And so then we can use that as a check to see that these things work.
We have a question over here. Let's see if I can bring it over here.
I was going to ask, how do you know the intelligence of an animal that is extinct?
So it has to do with, there's a few different things, but we do this actually with the ancestors to humans as well, and looking at human intelligence and hominid intelligence. It has to do with a few different measurements, but the relative brain, your skull capacity, so that gives us an estimate of brain size to body size. And so that ratio of brain capacity to body size, basically if you have a bigger brain relative to your body size, we assume you have a higher intelligence. And this is linking to what we know now, specifically with mammals, and of course our ratio changes across taxa, but we are able to measure intelligence in mammals and look at that relative, the idea of a pea brain is a real thing, right? Because you're not as smart if you have a smaller brain. And we've been able to look at that with human ancestors as well.
Yeah, and to add a little more to that as well, there are, as Katie mentioned, we can test things now, right? So you've maybe heard of some of the studies of what can crows do in a lab if we give them certain things and see how they work tools. And so we can combine some of that information. And then they also, so the particular ratios that we have in the slideshow also include adjustments for, if we think about whales or other things, right? That body mass doesn't quite work the same way because it's in water, and so we make some adjustments for things like that as well.
dinosaurs didn't, survive here and survive forever, could dinosaurs and humans coexist?
Yes, they already do. Right? How many of you are eating chicken right now? Right? Did you get chicken on anything? A sandwich, a pizza, or whatever, right? You're eating a dinosaur, right? So we do already kind of coexist. From the extent of like a large theropod that I would have to run away from, I don't know, right? There's a lot of climate, really, is what it would come down to, right? The Cretaceous was a lot different than we live now. So I don't necessarily think a lot of them would survive in the modern climate. You got to think about like niche partitioning and keeping up, enough prey items for a large predator like T-Rex and things like that. But from a standpoint of do we live with dinosaurs? Yes. It's a good question. So the question is, why do T-Rex have arms if they're useless? And I honestly don't know. Well, that's a great question. The joke, right, is that a T-Rex is basically just teeth with legs, right? So that's just what kind of won in the evolutionary arms race. So when animals are competing to survive, right, a predator is going to try to always outcompete the prey, and the prey is going to try to outcompete the predator, right? It's going to try to survive the attacks, and the attacker is going to try to come up with something new evolutionarily. And this is what was winning at the time, right? This large head with a lot of teeth was able to outcompete anything else and was able to be bigger and faster and meaner than everything else. And there's some debate on that the arms might have been used for mate attraction or for grasping prey or things like that, but there's not really much evidence for that. It's mostly that they use their mouth for everything.
So not necessarily related directly to the science, but you guys are all working on research in these areas. Do you have projects that students, undergraduate students, can be involved with? And if so, can you talk about some of those a little bit and how those students can get involved?
Sure. So maybe not so much on the dinosaur end. My areas, as Dr. Haas mentioned, is more hydro-environmental glacial. I'm looking at sinkholes in the area and trying to get measurements and make maps for the community, because there's not really something. Yeah. I also am working out at Austin Peay's Environmental Education Center and Farm to try to get a water supply for cattle. We have a well out there, but there's still some chemistry issues there. So if you want to get out in the field and do some water testing, that's an option. I'm actually going to let Dr. Harrelson talk for a minute, because I know he's got some research projects going on as well.
He's gonna stop doing that.
De facto joining. Sure, I can put in a little plug for it, actually. I'm looking for some students to help me out with the project this summer. I'm interested in getting to know the minerals you find about the state. If you've ever seen geodes and things in Tennessee rocks and Kentucky rocks, I want to know more about them and how they got there. And so the first thing I need to do is go out and find some more of them. Actually, if there are any rock hounds in the room, people who have, right. People with experience about the state that have any ideas about where to go finding geodes with fun minerals and things, I'd love to hear about it. In the ground. Yeah. Thank you, Alan. Perfect. In the ground, that's where I'll start. Yes.
If you're not a rock nerd and you like animals, I study mammals, and so I actually, most of the work that I do right now in Tennessee is with bats, which is why, bats are related to everything. But I will actually, we're starting a project looking at overheating in bat boxes, and so if there's undergrad students that want to help out building bat boxes, and then we're going to deploy some, we're actually going to be looking for locations to deploy bat boxes. So if you think you have bats in your backyard and you want a free bat box, definitely send me an email. Just Google Dr. Katie Haas, APSU. We'll just give you a bat box. So we'll be doing other bat projects this summer as well, but always looking for hands, basically. Any other questions? wait, we have one. Are you? Two more? We got two more questions. Wait, are you?
Careful, Katie.
It's amazing how much we learn from fossils, but how in the world did we figure out that T-Rex could see color from a fossil?
I'm gonna let that be good. I just got some pandas, so I don't know the answer to that. Is it has to do with like
So a lot of that stuff is going to come from CT scans and X-rays of the fossils, right? So something Dr. Dunkel mentioned is that we use X-rays in the lab, right, after the fossils are out of the ground. So you can do a lot of CT scanning and X-raying to actually see inside the fossil. And inside of a T-Rex skull is basically a smaller T-Rex skull, right? So the brain cavity is pretty well preserved in a lot of the specimens around the country. And so if you take CT scans of those, the impressions that the brain folds and things left behind inside the brain cavity, you can make measurements of those and kind of estimate, well, it would have had a large lobe for this, and based on modern animals, we understand this is for color vision, or this is for this, or this is for that, right? So it's going to be from actual measurement of inside the skull. It's a good question.
All right, thank you. What great questions. Wonderful. Can we give our speakers one more round of applause? Wonderful. Thank you. Now, I did want to mention, so this was such a fun class for Dr. Haas and her students. And I think everybody, I speak on behalf of all the guest speakers, it was so much fun to come in and talk to her class and her students. So we wanted to make this a bit of a series. So our April speaker will continue this series, Science in the Movies, Moneyball edition, with Dr. Matt Jones, who's actually here tonight.